So our
Start.
next speaker is Nelson Martins-Ferreira talking about categorical analysis of MATLAB and Octave programming functions. Take it away.
Okay, so thank you very much, and thank you for the invitation. I'm very pleased to be here. I didn't know that these seminars were being organized in such an organized way, and it's very nice. So I'm happy to go back and see the past ones since they are recorded. It's a very interesting thing to do. So for my talk, so here's the outline. Um, I will show very quick intro of MATLAB and Octave for those that are not familiar, and I will go directly to the functions that we will use. And then I will show two main motivations that came to the analysis of categorical structures modeling computational systems. So I will give a first idea of how could we define the category or a category of structured sets, so that the way sets are really encoded into a computer. So it's a mix between the category of set and its implementation in a computer system. So then I will explain in more detail what I mean by the MATLAB Octave category, and see some categorical properties, namely the functions unique and ismember. And then we'll see that in practice, the objects are being considered as, so the matrices are objects, and we'll see what morphisms are. And in the end, I will share a homemade implementation for two functions which are important, namely coequalizers and indexing D graphs, or graphs in abstract. So let me give you a short introduction to MATLAB or Octave. So I'm using Octave. So it's an online version. Everybody can have this. So I'll just run this application, and I've already predefined this thing. So here's what I want to show. So we can define anonymous functions. So for instance, for finding the divisors of a number, let's say 12, divisors of 12. We can use this. Well, is this going? You still see my screen?
Yes.
Okay, good. So this is a very basic introduction and very short. So just to say that we will use the colon operation to generate numbers from 1 to 12. This is the result. We can find the modular modulus function to find the divisors. And so basically, when we use this expression, mod n 1 to n, it gives the remainder of division by 12 in this case. And when we equate it to 0, it gives a logical vector. So this k is a logical vector which finds the positions where there are 0 in this vector. And when we use the function find, so find of a logical vector gives us the indexes where the positions are 1. All right, so that's how we extract the divisors of 12. And this will play an important role, namely the function find and sparse are kind of the inverse to each other, so that if we have the indexes and we define the function sparse with these indexes, then we extract back the logical vector. And all right, so continuing very quickly, we will see that this function, this built-in function unique, is actually a split epi strong mono factorization system. in computational language. And it can be actually understood in more basic terms. So it is actually built up of the more primitive functions, namely sort, diff for successive differences, and cumulative sum. So essentially, if we wish to determine the unique elements in this list, so what we do, let me continue here. So what we have is the unique function gives us the unique elements. R is a pointer to every unique element, and Q is identifying in the list of unique elements that are the same. So this is the structure that the function unique gives us, and we can understand it if we alternatively perform this set of instructions. So it works like you first order your list of elements, and then you take successive differences. You have the positions where the differences are, and then by cumulative sum, you recover back the original information and the indexes where a selected element for each unique index. All right, we will also see that it works for rows, so we can also interpret a matrix as a collection of rows and find unique rows in the matrix. Similarly, but each element is now a row. And then finally, we have the ismember. Let me run it. And so ismember will find for a given list of elements, which one is an element of a list of unique elements. And as we will see, this will be interpreted as a pullback. All right, so let me go back now to the presentation. So this is for shortly what I've just presented. Let me start with motivation. Okay, so one part of motivation in studying these structures came from a result that classified internal groupoids in terms of involutive two-links. So the result is that for any category, the category of internal groupoids is equivalent to the category of unital and associative involutive two-links. So what is an involutive two-link in any category? It is a structure consisting of a morphism, M, together with two endomaps of its domain, which are involutions, and they are intertwined in this sense. So there is a functor from every groupoid. We can extract an involutive two-link structure, namely, we just recover the multiplication or the composition of the groupoid. This is our M. And then we build up these two endomorphisms, with these two formulas. So we still remember the involution, the inverse map, but domains and codomains are completely forgotten. Okay? So, but since this is a full embedding, we can then characterize which involutive two-links are coming from internal groupoids, and then the result is unital and associative. So unital is a property that says that the pair M and M theta, together with the pair M and M phi, are jointly monic, and there exists two morphisms, E1, E2, which are uniquely determined by a list of axioms. I'm not showing these axioms. You can see it in the paper. And plus associativity of M. Now, this information is then used to reconstruct from such an involutive two-link an internal groupoid, and we define second projection as this. First projection, the inverse map is this formula. And as soon as we have pi1 and pi2, we take the push out and we get domain and codomain. And the morphism E is such that this condition satisfies. So this is just to show that there is some importance in studying this kind of structures coming from internal groupoids. However, it also comes from triangulated surfaces. So not exactly the same, of course, but in a similar fashion. So from this point of view, and so I'm also giving references, the references are in the abstract. So for a triangulated surface, set of vertices, edges, and triangles, we can encode it as a tree graph. So triangles, vertices, and the tree projections. So every element in T is interpreted as a triangle with the three vertices, A, B, and C, these three projections, and each one of them is realized into three-dimensional space. Now, when does such a tree graph comes from a triangulation? Well, this is well known. It's when there is a star neighborhood property, namely that around each vertex, if you take the collection of triangles incident to it, they can be ordered in a cycled way so that it forms a neighborhood homeomorphic to the disk. So the question is, can we trade this property of the star neighborhood by a structure so that we can then internalize it into a categorical context? And the answer is yes. Analogous to groupoids, we get a morphism G together with two endomaps, such that phi cubed is the identity, phi squared is this composition, and g theta is G. And what is the interpretation is, instead of triangles, we now look at edges. So this is now the collection of edges. Each edge is indexed, and phi is the following edge in each triangle. And theta is the adjacent edge in the adjacent triangle. And if you then take a look, these conditions, they are just encoding the star neighborhood property, which is now just saying that theta is bijective. All right, so this, all right, and this then can be generalized to polyhedral surfaces, not necessarily triangles, but any surfaces build-up of faces, which can be any polyhedral, not necessarily a triangle. And then it boils down to this simpler structure, which is interpreted as, again, A is an edge, and phi of A is, again, the following edge in this will construct the face, the polyhedral face. And then instead of working in R3, we just use complex numbers to use intrinsic coordinates. So it just encode how much an edge turns with respect to the previous one, and how much it expands or contracts with respect to the length of the previous edge. And now the property is that there should exist theta such that these conditions, and in that case, this is a triangulation, or more general, a polyhedral surface. Okay, this is a motivation to define a category of structured sets. And I've simplified a little bit. It is more there are more things to it, but essentially the objects are diagrams of this sort, where we have here a preordered monoid, which encodes the type of data. And you see the structure is, as it comes from this interpretation, but it's now considered as abstract, and this can also be modeled as the computational system of a set, from which we can then extract. So a set is a list in computer, which is encoded in a type of data, but it also has its structure. So the list is necessarily represented in memory in structure form. And this is encoded in this way. So there are two different interpretations, but the structure is the same. Morphisms are as expected, except that so we have to require that this morphism in the middle is compatible with the endomorphisms, this condition. And since this is preordered, we only ask this square to commute up to the order. And so actually at the end, we will see that one of the most important algorithms that we encounter is how to go back. So from any graph, we try to find this morphism phi such that codomain is determined by phi composed with the domain. But we also extract the intuition from a set. So namely, we look at the map G as so the set is in the image of G, and this is really recovered by taking the unique elements in the image of G by this unique morphism, as I've shown before. And it also models polyhedral surfaces, as I've said before. All right, so let us continue. About computational categories in the same light as I was saying before. So let me quickly give you an idea of a concrete example of discretizing the complex plane. So suppose we want to consider our type of data is complex numbers. And in practice, we have to discretize it. So instead of the set of complex numbers, we use a set of indexing maps. And so that each map, by some formula, has a realization into complex numbers. Then we can go back by retraction and then we can transpose the structure of complex numbers to this indexing set. And we still have some richness because we are not just using linear indexes. We are using maps which can be seen as strings of indexes. So there is some richness that can be used at this level. But of course, when as soon as we go back to the implementation, we linearize the indexes. So we no longer work with maps, but we work with indexes to those maps. And so the overall structure looks like this, where so we start with the complex numbers, we discretize it by some structure, and then we linearize. So this A is now just a set of indexes, is just linear indexes. And we have logical vectors saying that so if you think this A is kind of like the universe of our speech, but it is already indexed. So everything now is just indexes. So then we are interested in subsets of these indexes. That's why we have this logical vector, which is comparable to a list of unique entries. That's how we get from K, we get U by using the find K, and vice versa. Given U, we define sparse and we get the logical associated vector. And so we see that there are several things going on here. At this level, we think of this as a ordered set, and this is a map of ordered sets. At this level, we think of partial maps because this is the universe of indexes, but we are interested in subsets of the universe. So then we have to consider partial maps. And so we see that there is the category of finite, so fin, like modeling finite ordinals. And the objects are natural numbers. The morphisms are pairs, natural number and the vector. So this is really a MATLAB or Octave vector, which has to be equipped with a natural number for the codomain. since the domain is the number of its elements. And that's how we encode morphisms between ordered sets. Then partial maps are the same, except that they are allowed to be zero. And the subobjects are the logical vectors, which are also in correspondence with the vectors with unique entries. Now, interestingly, the partial maps can be seen as spans, as usual, but also there are nice functions that we can use to model it. So for a partial map, which is just a vector with zero or more, with entries ranging from 0 to some number, the domain is the number of elements of P, and then it decomposes as a monomorphism and a morphism with this structure. So this is how we analyze the category of MATLAB and Octave, namely its variables. Okay, very quickly, some categorical properties. So as I was saying, the function unique, which has this signature, given a vector v, it returns a vector u with its unique. This choice, of course, can be changed. So by default, it selects the first element of each unique index, but it could be the last or it could be different. But by default is the first element. Well, we have the subobject classifier as I said before. So given a logical vector k with the expression find k, we get its the map which is associated to its characteristic function, and giving a monomorphism by taking sparse, we take its characteristic function. This interplay between find and sparse can also be interpreted as moving from a relation as a subobject or a relation as a span or a graph, if it is from A to A. So the signature is like this. So given a binary matrix, when we do find, we extract D and C, and we move from the relation of the adjacency relation of the adjacency matrix of the relation to the graph, associated graph, and vice versa. If you have the graph, we move to the adjacency matrix by this function sparse. Okay, so then we analyze ismember. So the signature of ismember is ismember of a vector v, and a vector of unique elements m returns two vectors, k and p. K is a logical vector, p is a partial map, and it builds the pullback as follows. So from this partial map, we find its associated span. So this is just the find of p, which is the same as find of q, and p of find p, which is the set where it is defined, gives precisely the inverse image of G by M, and this is a pullback. Okay, now, in practice, we need to consider matrices as objects. So instead of the dual of the category of matrices as the usual objects, natural numbers, and morphisms are matrices, we consider objects as matrices. And how do we make it compatible with the previous definition of finite ordinals and subobjects and so on? Well, we consider a matrix as a collection of rows. So for our purpose, a matrix will be a map from the list of indexes of rows into Cn, and Cn is the length of, is the number of columns, the length of the rows. And morphisms are just morphisms between ordered sets of linear indexes, but with the property that there exists another morphism, G, such that this condition holds. And if you interpret it, this is equivalent to just saying that there exists some thing here making the diagram commute. But in the language of MATLAB and Octave, B and A are matrices, and F and G are indexing of that matrices. And it is just saying that this matrix is equal, and in MATLAB equal is this sign, to this one. So this is the valid MATLAB expression. And you can say that the morphisms are triples, A, B, F. A and B are matrices. F is just this indexing function, for which there exists G, such that this expression is a valid MATLAB expression. And then we observe that everything, so MATLAB and Octave are already prepared to work with this object, since we can use unique rows, ismember rows, and sortrows. Okay, I'm about to finish. I think. What about time? Is it on time, right?
Yeah, you still have a couple of minutes.
Okay. So just to say, as I was saying, an important application of this. So this is used in practice with solving real problems, and one of the problems is indexing. Given a graph. So a graph in this language is now two matrices, n by m. One matrix is interpreted as domain, another matrix is interpreted as codomain, and we wish to find an indexation of that graph. So just to work with indexes. And moreover, we would like that the domain map should be surjective, because, as I was saying, we will always be looking for an endomap of the domain such that codomain is encoded as domain composed with this endomap. So one of the necessary conditions for that is that T is surjective. And so we, using a combination of categorical methods with computational methods, we observe the following procedure. So given these two matrices, we first take unique indexes of the first matrix, the DOM matrix. So we perform this instruction. And then we use the ismember to take indexes in the codomain matrix corresponding to the ones which were already observed for the domain. And then we observe that this is a pullback, and we construct the desired indexation in this way, where we can also provide the user with some extra information, namely the original data. Okay, and so this has been implemented here. And so you see, okay, this is, okay, let me go here. So you see the function is like this. It has some preliminary data controlling. So if data is not appropriate, it has to do some preliminary stuff. But then the whole function is just a combination of unique ismember, as I was saying. So this is very powerful programming language. As soon as we understand and can mix the categorical interpretation with the computational system. And so to conclude, I would also like to share a very simple implementation of coequalizer. So given now a graph indexed by the previous procedure, and assuming that D is surjective, then also this very simple implementation provides us the coequalizer of this pair of morphisms. And I think I end up here. So if any questions, I'm happy to answer. Thank you very much.
Thank you very much for your talk. And if there are any questions, please to yourselves speak or type. Ivan?
So I wanted, this talk was very interesting, and I really liked it. I wanted to ask what brought you to this. Are you working on this kind of problems recently? Is this some kind of fun that you're having? What's your story with this?
Okay, yeah. So this was motivated. I've been working long time with these structures, and I've been observing some of these things, but sparsely. And then recently, I decided to take this to my students. And when trying to formalize it to the students, I really had to make it very precise. And yeah, in that moment, it became more and more evident that there was this very strong connections. And the nice thing is that if you interpreted because these functions unique and ismember and so on, I suppose they were not designed from a categorical point of view, because they are just practical for the practical things to have at end while you are programming. But the insight is that as soon as you realize that it can be interpreted as a factorization system, as pullbacks, and this correspondence between subobjects and graphs, spans, then you can use categorical ideas and conceptual understanding, and this simplifies a lot the implementations. So for instance, there were previous implementations of these functions, but they were much more cumbersome. So now it's really categorical in a sense. And so if I may add just one thing is this idea of what is a set, and a set for mathematicians is one thing, and for from computer sciences is perhaps a different thing. And this was uh, uh, an idea of to have a category whose objects can be seen as sets if you don't look at the structure. So if you just look at the image, the unique elements of your structure to memory with positions, then it is a graph, and it has some extra structures that you can extract. Plus the interpretation of surfaces as I showed. So essentially, there are several converging paths that arrive to this point. Yes.
Okay. And Zurab?
Hi, Nelson. Long time no see.
Hello. Yes, that's true.
Nelson, so did I misunderstand? So there are these specific functions that you gave categorical meaning to, but what about other functions, or is that not the goal? Or maybe these functions are the most fundamental ones?
Yes,
How much of the
there
programming
are.
language are we able to capture just by these the ones that you interpreted categorically?
Yes, there's probably it probably goes on and on. The thing is, probably we could categorize it even from more basic stuff. So when I say a type in the model I proposed, a type is a monoid, a preordered monoid. If we have some extra structure, which I didn't mention, that's why I call it simplified. But it somehow, if you have apart your ordered structure, by the way, this ordered structure is modeling is a prefix of, so x is less or equal to y if x is a prefix of y in terms of strings. But then you could also, in order to have successive differences and cumulative sums, which are very basic and sort, you need to have a linear order or a complete order. And this seems that this is at a very fundamental level. So I'm convinced that yes, there is a way to, there is a path to proceed and to try to define a categorical system, computational categorical system from very basic primitives.
Thank you.
Any other question? Okay, so let's start. Oh, Ivan.
Yeah, I have a super quick question. Are you writing a paper about this or not?
No, I'm just writing notes for my students.
Okay.
But I can share the notes, yes.
Okay, let's thank the speaker again.